দেখো আমরা লাস্ট ক্লাসে আলোচনা করেছিলাম সিএফটি ফর অক্টাহেড্রাল কমপ্লেক্স। আজকে আমরা আলোচনা করব সিএফটি ফর টেট্রাহেড্রাল কমপ্লেক্স। সিএফটি ফর টেট্রাহেড্রাল complex. All of you knows that tetrahedral complex are like this. Here is the central atom and 4 ligands are situated in this tetrahedral manner. In this tetrahedral complex, let M is a central atom and these are the 3 perpendicular axes: x-axis, y-axis and z-axis. In this tetrahedral complex, all the 4 ligands are come to the central metal atom in between the axis. That means if one of the ligand comes towards the central atom from this position, then one of the ligand comes from this area, one of the ligand comes from this area and one of the ligand comes from this area. And you know, in central atom or coordinate complex there is 2 type of d orbitals. One type of d orbitals are along the axis, dx square and dz square, and one type of orbitals are present which are in between the axis, like dxy, dyz and dzx. dxy, dyz and dzx. In these orbitals, some amount of electrons are present and ligands are also containing lone pair of electrons. Ligands are also having lone pair of electrons. So in this case, in this tetrahedral field, when ligands are comes towards the central metal atom, it is seen that those orbitals are along the axis. That means dx square and dz square, they face less steric hindrance, and dxy, dyz and dzx, these 3 perpendicular axes are face more steric repulsion, more electron repulsion due to their position. So it is seen d orbitals are splitted into 2 parts. First of all, these d orbitals are getting somewhat excited. Then these d orbitals are split into 2 energy levels. Energy level. In octahedral complex, we seen that dxy, dyz, dzx, these 3 orbitals forms lower energy level, and dx square and dz square orbitals are form higher energy level. But in tetrahedral complex, it is seen that the 3 orbitals dxy, dyz, dzx, which are in which are in between the axis, they are facing more repulsion and forms higher energy level. These energy levels are now called T2, and these energy levels are called E, and the energy gap between T2 and E is known as delta T. Delta T. This energy gap is known as delta T. Now, the difference of energy, that means delta T, is comparably very low than that of delta O. It is seen that delta T is approx about 40% of delta O. That means the energy difference between T2 and E is very much lower than that of octahedral field. So, when a central atom having electronic configuration D1, the electron come to first in E level, E energy level, E energy level. Then the electronic configuration of D1 complex in tetrahedral field is E1 T20, E1 T20. When a central atom having electronic configuration D2, both the electrons comes to the E energy level and electronic configuration becomes E2 T20. When a central atom having electronic configuration D3, now what will happen? In octahedral field we can see two possibilities are there, but in case of tetrahedral field only one possibility is there. They always forms high spin complex because the pairing energy is much higher than that of delta T. That means electron cannot combine fast. They first of all becomes unpaired condition. Then they are making pair. In tetrahedral field, pairing energy is higher than that of energy gap. So in D3, electron cannot combine, cannot making a pair. The first of all electron are going to the higher energy level and it has high spin. That means its electronic configuration is E2 T21. Then D4 E2 T22, D5 E2 T23. Now it is seen that all the levels, energy levels are having at least one unpaired electron. Now when a central atom having electronic configuration D6, then that electron comes towards the lower energy level, that means E. So its electronic configuration becomes E3 T23, D7 E4 T23, D8 E4 T24, D9 E4 T25 and D10 E4 T26. Next, we calculate CFSE, crystal field stabilization energy for tetrahedral complex. It is seen from this diagram that in tetrahedral complex all the complexes are high spin complex. There is no influence of ligand. In octahedral field, we have seen that due to presence of strong field ligand, complexes are become low spin complex, and due to presence of weak field ligand, complex are becomes high spin complex. But in case of tetrahedral field, there is no influence of ligand. That means strong field ligand and weak field ligand, both of them can forms only high spin complex. Now we calculate CFSE, crystal field stabilization energy for tetrahedral complex. You must remember that for each and every electron, when comes to the E energy level, they lose 0.6 delta T amount of energy, and when each and every one electrons comes to a T2 set, it gains 0.4 delta T amount of energy. When an electron comes to the E set, it loses 0.6 delta T amount of energy, and when electrons comes to the T2 set, it gain plus 0.4 delta T energy. Suppose a certain central atom having electronic configuration EX T2Y, then CFSE becomes X into minus 0.6 delta T plus Y into plus 0.4 delta T. It is the general equation of CFSE for tetrahedral complex. Now you can calculate CFSE from this electronic configuration. Let D1, what is the CFSE? 1 into minus 0.6 delta T plus 0 into 0.4 delta T, that means minus 0.6 delta T. What is the CFSE of D4? 2 into minus 0.6 delta T plus 2 into plus 0.4 delta T. So minus 1.2 plus 0.8, that means minus 0.4 delta T. By this way, we can calculate CFSE for tetrahedral complexes. Now we discuss the factors which involve for the energy gap of T2 E set or T2G E set. That means the energy gap is which one known as delta T or which one known as delta O for tetrahedral complex. Next আমরা আলোচনা করছি যে ক্রিস্টাল ফিল্ড যে শক্তির পার্থক্য সেটা কোন কোন বিষয়ের উপর নির্ভর করে। দ্য ফ্যাক্টর influence the delta, the energy gap delta. There are many of the factors which influence this energy gap. One of them is which d orbital is present of the central metal atom. When a central metal atom having 3d electrons, then the energy gap delta T or delta O is minimum. Then which having 4d orbitals, they have higher energy gap. than 3D, and which one having 5D energy, 5D orbitals, they have maximum energy gap. That means 3D, 4D and 5D. তাহলে 3D কক্ষকের শক্তি পার্থক্য হবে সবথেকে কম, ডেল্টা গ্যাপ, নেক্সট 4D, নেক্সট 5D। নেক্সট দেখো চার্জ অফ আয়ন, charge of central metal ion. It is seen that which metal having higher charge density, higher positive charge density, having much energy gap, যাদের ক্ষেত্রে তোমার ধনাত্মক আধানের পরিমাণটা বেশি থাকবে তাদের ক্ষেত্রে ক্রিস্টাল ফিল্ড শক্তির পার্থক্য ডেল্টা এর মান বেশি হয়। দোজ সেন্ট্রাল অ্যাটম হ্যাভিং মাচ হায়ার চার্জ, দে আর অলসো হ্যাভিং হায়ার এনার্জি গ্যাপ। লাইক in a particular complex, Fe is in Fe2 plus state, and in another complex Fe is in Fe3 plus state. So the delta value is seen that Fe3 plus is higher than that of Fe2 plus. তাহলে আমরা কি বলছি যে Fe2 plus এবং Fe3 plus দুটো আয়নে যদি উপস্থিত থাকে, তা Fe3 plus এর ক্ষেত্রে আধানের পরিমাণটা যেহেতু বেশি, তার জন্য দেখা যাবে এর ক্ষেত্রে ডেল্টা অর্থাৎ শক্তি পার্থক্য যেটা সেটা কিন্তু বেশি হবে। Next, geometry of the complex. Geometry of the complex. In tetrahedral complex, the energy gap delta T is 40% about 40% of energy gap of octahedral complex. So geometry influence the energy gap. তাহলে আমরা কি বলছি যে টেট্রাহেড্রাল কমপ্লেক্সের ক্ষেত্রে তোমরা দেখলে যে ডেল্টা টি এর মান ডেল্টা ওর 40% মতন হয়, 40% মতন হয়। তাহলে যদি 40% মতো হয় তার মানে কি হচ্ছে গঠনাকৃতিটা, জটিল আয়নের যে গঠনাকৃতি, the structure of the complex, geometry of the complex influence the energy gap between two energy levels, that means E T2 or T2G Eg. Next, influence of ligand. Influence of ligand. Ligandের প্রকৃতি। Ligand is one of the important role in the separation of energy levels. In tetrahedral complex, we have seen that there is all complexes are high spin complex because value of delta T is much lower than that of pairing energy for each and every ligand. But in octahedral complex, we have seen that they have two types of energy levels. When strong field ligands are there, then it is seen delta O value is much higher than that of pairing energy. The delta O value is much higher than that of pairing energy. And when weak field ligand, we can see that pairing energy is much higher than delta O. So the influence of ligand for the energy gap is most important. এই যে আমাদের বিষয়টা, এটার উপর ভিত্তি করে আমাদের একটা স্পেকট্রোকেমিক্যাল সিরিজ তৈরি করা হয়েছে। উই ক্যান ফর্মস এ স্পেকট্রোকেমিক্যাল সিরিজ হুইচ ইন্ডিকেটস হুইচ ওয়ান ইজ স্ট্রং ফিল্ড লিগ্যান্ড অ্যান্ড হুইচ ওয়ান ইজ উইক ফিল্ড লিগ্যান্ড। It is called spectrochemical series. Spectrochemical series. According to this series, carbon monoxide is the strongest ligand. Then comes Cn minus. Then comes triphenylphosphine. Then comes NO2 minus. Then En. So on. En. Next, you can say NH3, so on. And weak field ligands are like Cl minus, SCN minus, S2 minus, Br minus, I minus. These are the weak field ligand, and these ligands are strong field ligand. কি বললাম বুঝতে পারলে? তাহলে লিগ্যান্ডের প্রকৃতির উপরেও আমরা দেখব যে এই যে ডেল্টা টি, ডেল্টা ও, এই যে ডেল্টা ভ্যালুগুলো, এই মানগুলো কিন্তু নির্ভর করছে। স্ট্রং ফিল্ড লিগ্যান্ড এর মধ্যে আমরা উদাহরণ হিসেবে দেখছি কি কার্বন মনোক্সাইড, Cn minus, PPH3, NO2 minus, En, NH3. All these are the strong ligand, and this series is continuing series, and Cl minus, Sn minus, S2 minus, Br minus, I minus. These are the weak field ligand we can say from this spectrochemical series. Now we study color of coordination compounds. Color of coordination compound. Color of coordination compound due to DD transition. DD transition. What is DD transition? When some amount of electrons are present in the central atom in coordinate complex, we can see these energy levels are split into, these two d orbitals are split into two energy levels, T2g and Eg. T2g is the lower energy level and Eg is the higher energy level for octahedral complex. Suppose one of the complex in which the central metal atom containing at least 1 d electrons. If 1 d electron is present, after splitting this d electrons comes to the T2g set. T2g সেটে এখানটায় ইলেকট্রনটা অবস্থান করবে। Then by accepting proper energy, this T2g electrons comes to the Eg energy level. From lower energy level it comes to higher energy level, but this energy level is not feasible, not stable. So this electron this higher energy electron again come back to the initial energy level. When these excited electrons come back to the ground state, it lose some amount of energy and which produce a particular prominent color. So it is known as DD transition. কি বললাম যে নিম্ন শক্তি স্তরে যদি ইলেকট্রন থাকে, সেই ইলেকট্রন উপযুক্ত শক্তি গ্রহণ করে উপরে কক্ষপথে চলে যাচ্ছে, উপরের শক্তি স্তরে চলে যাচ্ছে। সেই উপরের শক্তি স্তর থেকে ইলেকট্রনগুলো আবার কি হবে, নিচের শক্তি স্তরে ফিরে আসবে। আর নিচের শক্তি স্তরে ফিরে আসার সময় এ কী করছে না, তো কিছুটা পরিমাণ শক্তি ছেড়ে দিচ্ছে। তাহলে এই ঘটনাটাকে আমরা বলছি ডিডি ট্রানজিশন। এই ডিডি ট্রানজিশনের জন্যই আমরা দেখি বর্ণ তৈরি হয়। সো দোজ কমপ্লেক্সেস হ্যাভিং ইলেকট্রনিক কনফিগারেশন D1 to D9, all of them, all of these complexes shows color. But complex contain D10 electronic configuration, it cannot shows color. It cannot shows color because in D10 configuration all the orbitals are fulfilled. All the orbitals are fulfilled. So the lower energy electron cannot comes to the higher energy level because there is no space for electron. But if the electronic configurations are D1 to D9, at least one electron comes to the higher energy level. At least one electron comes to the higher energy level, and this higher energy electron again coming back to the lower energy level. When this phenomenon is happened, they lose some amount of energy like light energy. That's why when the DD transition is possible, then that complexes are becomes colored complex, and when DD transition is not possible, those complexes are becomes colorless, that means white in color. তাহলে কি বললাম যে D1 থেকে D9 কনফিগারেশন যদি থাকে তাহলে সেগুলো বর্ণযুক্ত হবে, কিন্তু D10 হয়ে গেলে সেটা বর্ণযুক্ত হবে না। আর কোনটা বর্ণযুক্ত হবে না? if the electronic configuration of a complex becomes D0, that means there is no electron in central atom. So DD transition is restricted, DD transition does not happen. So those complexes having D0 and D10 configuration, they does not show color, but those compound having D1 to D9 configuration, they becomes colorful due to DD transition. D0 and D10 does not shows color. D1 to D9 shows color. D1 to D9 shows color. D0 to and D10 does not shows color. Now we take some examples. Sc H2O whole 6 3 plus is a colorless complex. Why? In case of SH2 whole 6, 6 into 0 equal to plus 3, x equal to plus 3. Electronic configuration of scandium is 3d 4s2 3d1, but in case of SC 3d1 4s2 3d1 4s2. So in case of Sc3 plus, 2 electrons from 4s and 1 electron from 3d are evacuated. So electronic configuration becomes 3d0. When this configuration comes, there is no electron to the central atom. So DD transition does not happen. So SCH2 whole 6 3 plus, this complex becomes colorless. Again we take an example. Zn NH3 whole 4 2 plus. Zn is plus 2 state in this complex. X plus 4 into 0 equal to plus 2. The atomic number of Zn is 30. Electronic configuration is 3d10 4s2. In Zn2 plus complex, it's become 3d10 4s0. So when Zn2 plus all the orbitals are fulfilled by these 10 electrons. So dt transition does not seen. So it is seen that Zn(NH3 whole 4 2 plus is a colorless complex. তাহলে যাদের ক্ষেত্রে D0 বা D10 কনফিগারেশন থাকছে তাদের ক্ষেত্রে ইলেকট্রনের স্থানান্তরণটা সম্ভব হচ্ছে না, আর ইলেকট্রনের স্থানান্তরণ সম্ভব না হওয়ার জন্য এগুলো বর্ণহীন অবস্থায় থাকছে। This is colored complex. Why this is a colored complex? Because the oxidation state of nickel is +2. It's +2. Electronic configuration of nickel is 3d8 4s2. So electronic configuration nickel +2 is 3d8 4s0. In case of 3d8, it is seen the energy levels, higher energy levels are not fully occupied. So one of the electron from lower energy levels comes to this higher energy level, and from this higher energy level it again comes to the lower energy level. That means dd transition is happened in this case. এখানে আমরা দেখছি কি নিম্ন শক্তি স্তর থেকে ইলেকট্রন উচ্চ শক্তি স্তরে যাচ্ছে, আর উচ্চ শক্তি স্তর থেকে ইলেকট্রন নিম্ন শক্তি স্তরে ফিরে আসতে পারছে, অর্থাৎ dd ট্রানজিশন এখানে ঘটছে। আর dd ট্রানজিশন ঘটছে মানে এটা কিন্তু একটা রঙিন যৌগ হবে। CuSO4 5H2 5H2 copper sulfate, hydrated copper sulfate, all of them, all of we know this, it is a bluish in color. তুতে বাংলা যেটাকে বলা হয় তুতে, এটা হালকা নীল বর্ণ হয়। But when it is strongly heated, it becomes CuSO4 plus 5H2 is lose all of this water molecule. It is blue in color and it becomes colorless. Why? এটা নীল বর্ণ ছিল কিন্তু উত্তপ্ত করলাম তখন এটা বর্ণহীন হয়ে যাচ্ছে। In CuSO4, Cu is in +2 oxidation state. (3d10 4s1). So in Cu2 plus 3d9 4s0, 3d9 configuration, that means it shows dd transition. Still, when we heated copper sulfate strongly, it becomes colorless. Why? Because these water molecules behaves like a ligand in this case. এই পাঁচটা জলের অণু এখানে লিগ্যান্ড হিসেবে কাজ করে। But when we heated strongly, all the 5 ligands, all the 5 water molecules coming out from the complex. পাঁচটা জলের অণু কমপ্লেক্স থেকে বেরিয়ে আসছে। So without complex, without ligand, dd splitting does not occur. In case of CuSO5H2O, it's split into 2 energy levels. But without water molecules, these d orbitals does not make any split, that's why uh, hydrated copper sulfates becomes blue in color, but dehydrated copper sulfate is becomes colorless.